Okay, and now it's recorded. Perfect. All right, so let's start. Yeah, so we are still in section 3.2.
Hi, Professor. This is Jasmine. You got me for attendance?
Yes, I got you. Yeah.
All right. Thank you. All right. Thank you, Professor.
So, so we are still in the section 3.2, the measures of spread or measures of variation, right? Measures of spread. Okay, so just to remind you, so we discussed as a measure of spread, we discussed the range. First, the range, and the range, we said it's just the difference between the largest and the smallest data values, right? And then we have the standard variance and the standard deviation, right? The standard deviation S, standard deviation. Okay. And we said the problem with again, so the idea of the standard deviation. So what you need to keep in mind is that the standard deviation is just the average of the distance between your data and me, which is the expected value, right, of your data values. Now we said the problem with the standard deviation is that the standard deviation depends on the units, right? So if you have like two samples from different populations, like I don't know, a sample which represent, let's say, flowers diameters, right? So the unit would be inches, and the second example, which is, or the second sample, which is, let's say, which represent the weight of students, for example, in the class or something, right? So then the weight, of course, it's gonna dip. The units would be the pounds or kilograms. So we are using two different units, right? So then you cannot really use the standard deviation to compare the spread of the two data, the data values, because we are using two different units, right? So then we said the solution is to use, instead of the standard deviation, we can use the coefficient of variation, right? So the advantage coefficient of variation, right? So unlike the standard deviation, coefficient of variation is actually independent of the units, right? So if you have two samples from different populations, right, then you can use the coefficient of variation to compare the variation or the spread of the two data. All right, and then so we are done with the coefficient of variation, and then now we are trying to discuss the Chebyshev's theorem. Okay, so now this Chebyshev's theorem, we said, I mean, it already have to memorize this Chebyshev theorem, but what you need to keep in mind, guys, is the consequences of the theorem. Okay, so so we had a couple of consequences. So first consequence, so consequence. Consequences of this Chebyshev's theorem. All right. So first, we said, so we can say, so we have the following. So we know that from this Chebyshev theorem, we know that at least 75% of your data values of the data fall in the interval x bar. So the interval would be x bar minus 2s. The s is a standard deviation, x bar is the mean, right? And x bar plus 2s, right? If you want to do better than 75%, then the next percentage would be 88. And again, this is a consequence of the theorem. You can do better than 75%. So the next percentage is actually 88.9%. You can say that at least 88.9% of your data fall in the interval x bar minus 3s and x bar plus 3s. I see there's a question in the chat. Chat. Edward, you're here. Okay. Thank you, Edward.
Excuse me, Professor.
Yes,
So
yeah, please.
these percentage are standard. The
Yeah,
75%,
standard, yes.
9%, and I forgot the third one.
Yep.
That's standard. And let's say you want to know a specific one in the test. That's what you're going to ask for. Like what's
Yes. Yep.
89% of XYZ.
Yeah, so the percentage is going to be given. So I'm going to show you like in a couple of minutes with the examples. So for example, I don't know, like you're going to have like in the problem, you need to find let's say at least 75% of your data, or 88.9%, or next percentage is actually 93%. So the percentages actually are fixed. Okay, so they are, as you said, they are standard. But the thing is, so each percentage corresponds to a different interval. So like the 75%, the 75% corresponds to the interval x bar minus 2s, x bar plus 2s. The 88.9% corresponds to the x bar minus the s, x bar plus the s. So like in the problem, if you see, let's say 75%, then the interval you need to use is the x bar minus 2s, etc., x bar plus or minus 2s. If you see 88.9% in the problem, then the interval you need to use is this x bar plus or minus the s. So the interval depends on their the percentage. But as I said, as you said, the percentage is actually kind of fixed, so they are a standard. So another percentage or next percentage would be 93%, and 93% would correspond to of data. They fall in x bar minus or plus for s of the data fall in x bar minus for s, x bar plus for s. Okay. So, all right. So let's do a couple of examples. So example one. So I'm going to take the following. So suppose we have the following data. We have the following data. Okay, let's say we have five, we have 10 numbers. Okay, we have 10 data values. 5, and then 6, 7, 8, and 4 sixes. So as you can see, we have 10 numbers, right? We have 10 data values. Okay, we have 10 numbers. Now, what's the x bar of this data, the data set? The x bar, I mean, we know how to compute x bar, right? It's the sum of the values over the number of data values. Like here, that would be like x bar would be like 5 plus 5 plus 5, plus 6, 8, and then you have like 4 sixes, and then we're gonna divide by. We have 10 numbers, so we divide by 10, and I think the answer would be 60 over 10. So the mean x bar is 6. Okay, and then we are supposed to compute s, the standard deviation, right? Standard deviation s, and we know how to compute the standard deviation s. S. So in this case, I mean, it's gonna take probably like at least 5-10 minutes to compute the standard deviation, but the answer for the standard deviation here would be actually 0.93. Okay. Again, I'm not doing the standard deviation here because it's going to take me at least 5-10 minutes. Okay, but we do know how to compute the standard deviation, right, from the previous lectures, right? Now, so this is the answer for the standard deviation. So what I am saying with this Chebyshev theorem, for example, it says at least 75% of the data values, they fall in the interval x bar minus 2s and x bar plus 2s. So what does it mean they fall in the interval x bar minus 2s, x bar plus 2s? It means that the data values, they're going to be between x bar minus 2s and x bar plus 2s. So what's 75% of the data values? So what do we mean by 75 of data values? So how many numbers we have? We have 10 numbers, right? So when I say 75%, so we are saying 75% of the 10 numbers, they fall in the interval. So the theorem says, so 75%, remember percent means division by 100, right? Of the data values. Okay, so what do we mean by 75% of data values? 75%, that's 75 over 100, right? Times off. When you see the word off, that's a multiplication. That's a multiplication, okay? So times data values. How many data values? We have 10 numbers, right? We have 10 data values. We have 10 numbers, right? So 75 over 100 times 10, because I have 10 numbers. So that will be my 75% of data values. So 75 over 100 times 10, that's 75 times 10 over 100. So that's 750 over 100. So that's 7.5. Okay. So the theorem says at least we have 10 numbers, but the theorem says like at least 7.5 numbers are between. So at least 7.5 numbers or data values are between. So 75% corresponds to the interval. We said 75%, that would be the interval x bar minus 2s, x bar plus 2s, right? So between x bar minus 2s and x bar plus 2s. So like here in this example, what's x bar? X bar, we said the mean. We said the mean is 6, right? So it's 6 minus 2s minus 2 times s. S is standard deviation. It's 0.93, right? So it's 2 times 0.93 and comma. This is like for, this is interval notation. So this is like saying this is like the interval from, so this is the interval from x bar minus 2s to x bar plus 2s. So 6 plus 2 times 0.93. Okay, so that'll be equal to 6 minus, so 2 times 0.93, that's 1.84. Sorry, 84. Sorry, 80. I mean 86. Sorry, 86. 86, and then 6 plus 1.86. Okay, so then the answer, this is so this is the interval. So 6 minus 1.86, that's 4.14, and then 6 plus 1 plus 1.86, that's just 7.86. So what we are saying is the theorem says here at least 7.5 data values, and again we have the 10, not just 7.5, but at least 7.5 data values are between these two numbers, are between 4.14 and the 7.86. So at least 7.5 numbers are between 4.14 and 7.86. So the question is, how many numbers are actually between 4.14 and 7.86? Between 4.14 and, let me write it down here, So 4.14 and 7.86, sorry, 7. And 7.86. Okay, any guess, guys, how many numbers are between these 4.14 and 7.86? I mean, for example, we take 5, right? 5 is between 4.14 and 7.86. Again, 5, 6, it's also between 4.14 and 7.86, right? 7, it's also between 4.14 and 7.86. Now, 8, is 8 between 4.14 and 7.86?
No.
No, right? It's larger than 7.86. So 8 is not between these two numbers, right? 6 is, it's between the two numbers. So actually, that not just 7.5 numbers are between the 4.14 and 7.86. Actually, in this data, 9 numbers, not just 7.5, but actually 9 numbers.
Wouldn't that make it incorrect though? Because it's not including all the data values that we have.
Yeah, but the thing is, there's this word at least. It says at least 7.5. So the at least means like the minimum.
Right.
You know,
Okay.
at minimum, you know that at minimum, you have 7.5 numbers. Well, like 7 numbers and a half between these 4.40 and 7.86. But actually, it's more than that. It's actually 9 numbers. We have 9 numbers. But as I said, the thing is with the theorem, it gives you like the minimum at least, right? So of course the theorem is correct. Here we have more than 7.5. We have 9 numbers. So here we have 9 numbers. We have actually not just 7.5, but we have 9 numbers. We have actually 9 numbers or 9 data values between the 4.14 and the 7.86. Okay. So again, in some sense, the theorem predicts like the minimum number of your data values between your X bar plus or minus a multiple of the standard deviation. Okay. So the idea here, like in the exercises and the practice, guys. So in the problem, you're gonna see like a percentage. So I mean, most of the time it's gonna be either 75% or 88.9% or 93%. Okay, and the thing is, for each percentage, we have a different interval. Okay. Okay, so here's an exercise. Let's do an exercise, another example or exercise. So this example just to explain the theorem. It's not an exercise. It's just to explain the theorem. But now let's do another example, an exercise. For example, let's say we have a random sample. We have a random sample with X bar. I'm gonna suppose that X bar is equal to 15, okay? And standard deviation S standard deviation S equal to, for example, let's take 1.5. Okay. So the question is, find, let's say, the 93% Chebyshev's interval in this problem. Okay, so what we do is, you see, so the percentage is given, so it's 93%, and so it's 93%, right? So if you have 93%, then the interval, the corresponding interval, to 93%, it's X bar minus 4S and X bar plus 4S. So then the answer would be this interval, X bar plus or minus 4S. So the answer it's actually X bar minus 4S, comma, X bar plus 4S. Okay. Now we need to compute the X bar minus 4S, X bar plus 4S, and the X bar it's given, S is given. So like in general, in the homework or in the test, guys, you have your X bar, you have your S, and then the problem is going to ask you to find like the 75% Chebyshev's interval, or the 88.9% Chebyshev interval, or 93%, etc. Right? So like here, as I said, in this problem, we have 93%. So the corresponding interval is X bar plus or minus 4S. Now we need to compute this interval.
45-61.
Fecha de nacimiento. Probably I need to unmute someone. So X bar, it's 15, right? My X bar, it's 15, and then minus 4 times, and then we multiply by S, 4S, 4 times S. It's S is a standard deviation is given, it's 1.5. So it's 4 times 1.5. So this is like the lower bound. The upper bound would be X bar. X bar again, it's 15 plus 4 times 1.5. So this is just, of course, you multiply first, that's rule. So it's 15 minus 4 times 1.5, that would be 6. Okay, and then so 15 plus 4 times 1.5, again, it's 6. Now, so the lower bound 15 minus 6 would be equal to 9, and upper bound it's 15 plus 6, that's 21. And that's it, you're done. Okay, so again, so what we are saying here is that at least 93% of your data values, they're gonna be between 9 and 21. Okay, so so you're done with the exercise. So all you have to do, guys, is to find the interval, right? Once you got your interval, you're done. But again, the idea here is that, so what we are saying here, so the idea here is that what we are saying is at least 93% of your numbers, of your data values, are between 9 and 21. Okay. Any questions so far, guys?
So every problem is going to give us
Yes, the percentage.
bar and the standard.
Yes. So in every problem, you're gonna have your the percentage, the Chebyshev's percentage, and as I said, most of the time it's just you have like, I mean, what you need to keep in mind is this 3 percentages here, right? That's 75%, right? So let me write it down here again. So here, so what you need to keep in mind. So if you see 75%, then in your answer, the interval you need to compute is X bar minus 2S, X bar plus 2S. If you see 88.9%, right, then the interval would be X bar minus 3S, X bar plus 3S. If you see 93%, then the interval would be X bar minus 4S, X bar plus 4S. Of course, you can go, I mean, you can use the theorem to compute like, you can do better than 93%, right? But I mean, like in this course, we're gonna just use these three percentages. Okay, this is like the most common percentages. Okay, 75, 90, 80.9, and 93%. Okay, but of course you can use the theorem to to get the next percentage, which corresponds to, let's say, x bar minus 5s and x bar plus 5s, etc. Okay, so you can go, of course, in 93%. Okay, but for the purpose of this course, just we're gonna just use these three percentages. Okay. So here's an exercise. So here's an exercise for you. All right, let's do a couple of exercises. So exercise 1. All right, let's see. Okay, so exercise 1, consider a sample data. This is from the textbook. Not sure which number, but anyway, so consider sample data with x bar. So the mean, of course, x bar, that's the mean. It's equal to 20, and s, the standard deviation s, is equal to 2. Okay, so please try to compute 88.9% Chebyshev's interval around x bar. Okay, so I'm gonna give you a couple of minutes, guys, to think about this exercise. I can write down next exercise. I can probably write down 2 exercises here. Next exercise, and I will go over the 2 exercises. I think there's a question in the chat. Let's see. You're lost, Kyla? No, it's not. It's not.
Yeah, I'm lost. The only thing I got, I know that we're gonna put those formulas, but then everything after that, you think because I missed half the video yesterday?
Okay.
That's probably why, because I'm real lost. So I'm just gonna watch.
Watch.
I
Okay, no
can't.
problem.
I'm
Okay, no problem.
confused.
But the idea, you see this percentage?
Yeah,
The 88.9.
yeah.
And I was saying this 88.9 actually corresponds to this interval, the x bar minus the s, x bar plus the s.
Yeah,
So
no, I know we do all of those. Like
Okay.
if you see the 75, the 88.9, the 93 point, well, the 93% or whatever, but I'm having a problem after knowing the formula, computing it.
Okay.
Yeah.
I mean, the idea is to compute, of course, this interval. You see this this one here in the blue circle, the x bar minus the s, x bar plus the s. So all you have to do is to compute this interval. X bar, you know x bar is given and s is given, right? So all you have to do is to compute x bar minus 3 times s and x bar plus 3 times s. Anyway.
But is it really, it's not 3 though, is it? It is?
It is. That's the theme.
All right, so, okay. I'm still confused.
No problem. I mean, I will go over that problem.
Okay.
Well, actually, I see some answers in the chat. Yanni, you're saying 1426. Yeah, that's yeah, that's yeah, Samantha.
That was right? That's
Yeah.
good?
Janine, Samantha, you're right. Yes, you're right.
Okay, I'm just making sure I'm doing it right.
Yeah.
Thanks.
Okay, let me write down another exercise. All right, a random sample. This is a real world problem, I guess. A random sample, the sample of received 4 individuals eating at Applebee's restaurant. Restaurant had a sample mean sample mean X bar equal to $10.38. Okay, that's the mean of the. So we have the sample of receipts from people eating at Applebee's, right? The mean of the receipts is $10.38. That's not too much, I guess. And then and we computed the standard deviation as is $2. The standard deviation is $2.17. So the question is, find the smallest interval in which we can expect at least 75% of the meal receipts to fall.
Oh, I see. So it would be like 3 minus 217, right? Or no?
Yep. So it's well, here it's not 3 because okay, it's the percentage is 75%, right?
Mhm.
So when it's 75%, we said it's not 3, it's actually 2. So it should be like X bar minus 2 times S.
Oh, I was looking up at exercise 1, that's why. Okay.
So,
But what happens if like, could the number, like, you know how when S is given,
Mhm.
what if the number that you have to like is bigger? Like you can't take nothing from it. Like it wouldn't even add up. Like,
you mean
we'll
like a
always-
negative?
Yeah, like could it
No,
be?
it's fine. It's fine. If you end up with a negative number, that's fine.
Oh, okay.
You can have a negative number. Yeah, for sure. Yeah. I see there's an answer in the chat. I mean, you're saying, let me check the answers. Yes, very good, Danny. Yes, that's the answer. So, I mean, the idea here of the Chebyshev theorem is that you can see with this theorem that the S, the standard deviation, right? In some sense, the standard deviation controls the spread of your data values about the mean, right? Because these intervals, the X bar minus plus 4S or plus or minus TS or wherever, right? So those intervals are, around your mean, okay? So the standard deviation in some sense tells you, I mean, gives you an idea about the spread of your data values around the mean, okay? Right, so I got, for number 2, I got Yanin answer. Does anyone else has an answer for number 2? gonna go up here. So, I mean, as I said, it's a straightforward. You see the percentage, right? Then for each percentage, we have like a corresponding interval around the mean.
So do I do 75 by 100, 75 divided by 100?
No, you don't do.
No?
No, you don't. No, you don't have to do that. I mean, I was the 75 over 100, etc. That I was trying to explain the you know, the idea of the theorem. It's like 75% of your data values, etc. No, but all you have to do is just to compute the interval. You see the x bar minus 2s, x bar plus 2s, or x bar minus 3s.
Is the X bar the data values?
No, x bar, that's the mean. So x bar,
Oh,
that's the mean. That's our notation for the mean.
yeah, I should know that. All right.
And the s, that's the standard deviation.
And the standard deviation is the numbers in between, right?
Yep.
I think I need remedial math.
I mean, this is, I mean, you know, you have the formula and just, it's just basic operations, right? I mean, subtract, multiply, but of course you need to know your notation, like x bar. If you know the x bar, it's the mean, then
So I'm just adding it all up.
Yep. So yeah, so like for the first exercise, so for exercise 1. Exercise 1. So what does it say? Well, you need to find this 88.9, right? Chebyshev's interval. So you see the 88.9%? Well, 88.9%, sorry. Oops. Sorry about that. So the 88.9%, so as you can see, 88.9%, the corresponding interval, it's x bar minus the s, x bar plus the s. So what you have to compute is this interval, x bar minus the s, x bar plus the s, right? So exercise 1, I have 88, we have 88.9%, right? So then what we need to compute is x bar minus the s and x bar plus the s. The mean minus 3 times the standard deviation, and then the mean plus 3 times the standard deviation. Okay, so once you see the percentage, you need to know exactly which interval, Chebyshev interval, you need to compute. So, so we have x bar minus the s, x bar plus the s. Now, what's x bar? That's the mean. Now you check your exercise and see what's the value of the mean. Well, like in exercise 1, it says consider sample data with x bar equal to 20. So you know that the mean is 20, x bar is 20, and the s is 2. Right? They are given. X bar and s are given. So you know that x bar is 20 and s is 2.
So then you do 20 minus 3s.
Yes, 20 minus 3s. So s is, we said it's 2, right?
Yeah.
So 3 times 2. When I say 3s, it means 3 times s, right? The 3s, that's 3 times s. And then, comma, and then we have 20 plus 3 times s. So 3 times 2.
Okay.
Okay. Now, of course, PEMDAS rule, you need to multiply first, right? The 3 by 2, that's 6. So it's 20 minus 6. And the upper bound, it's 20 plus 6. So then 20 minus 6 is 14. And then 20 plus 6 is 26. And then you are done. That's it.
Oh, okay.
Okay. And again, the idea is, so this is the answer, right? You are done. But again, the idea is, what we are saying here is that at least at minimum, 88.9% of your values, of your numbers, are between the 14 and 26. So it gives you the proportion of data between 14 and 26. It's actually 88, at least 88.9% of your data between 14 and 26. Now, this is for the first exercise. So the exercise 2, you see the percentage is different. So in the exercise 1, the percentage is 88.9. Exercise 2, the percentage is, as you can see, it says 75%, right? So 75%, the corresponding interval, it's not the same. It's different from 88.9. So for 75%, the interval is x bar minus 2s, x bar plus 2s. Okay. So for exercise number 2, so exercise 2, so the percentage is 75%, right? And 75% corresponding interval would be x bar minus 2s, not the s. It's x bar minus 2s, x bar plus 2s. Okay, and then what's x bar? Well, it's supposed to be given in the problem. So this is problem number 2. It says x bar, it's $10.38. And the S is $2.17. So the X bar is 10.38. So it's 10.38 minus 2 times the S. The S, we said it's $2.17. Right? So it's 2 times 2.17. So 2 times 2.17. Now for the upper bound, so we have 10.38 plus now, right? 2.17. So of course, we multiply first. So it's 10.38 minus, so 2 times 2.17, that's 4.34. Oh, it's not 34. Why did I write 36? 34, comma, and then, oh, sorry, I forgot to multiply by 2 here. This is 2 times 2.17, of course, minus 2 times, sorry, plus 2 times 2.17, right? So it's 10.38 plus 4.34. All right, and then now we subtract 10.38 minus 4.34, so it's 6.04, right? Just the difference between 10.38 and 4.34. Now on the upper bound, so it's actually, I think, 14.72. If I'm not mistaken. Okay. So yeah, and then you're done. Okay. So that's the Chebyshev interval corresponding to 75% in this problem. Of course, so the X bar and the S, they depend on the problem, right? X bar and S, the mean and the S, they depend on the problem, right? For each problem, you have like different mean X bar and different standard deviation S, right? Any question, guys? Does this make sense to you? So anyway, so like in the test and the homework, just I mean, my advice is just, you can write down these 3 percentages and the corresponding intervals. Right? We have like basically 3 percentages here, and we have like 3 intervals, right? All right, guys. If there's no question, then we are done actually with this section, measures of spread. We can move to the next section, I guess. So that will be section. So I'm going to jump to the section 4.1. Okay, scatter diagram. okay, and linear correlation. Okay. So we have seen different ways actually to represent data. Remember, we have this frequency tables, we have these histograms, we have the ogives, right? Now we're going to see another way to represent the data, okay? And that will be the scatter diagram. Now, the thing about scatter diagrams, they represent data where you have like two different values, not just one. So for example, so the idea here, so the scatter diagram, the scatter diagram is a graph. That's a graph where the data is given by not just one value, but the data is going to be given by like a data pairs. So we're going to have like two values. The data is given by data pairs. Let's say X and Y, plotted using like X-axis, using X-axis and Y-axis. Okay. So, for example, let's have a explicit example. Okay. So let's say we have the following data where X, so we have the following data. So in this data, the X is going to represent the magnitude of an earthquake. So this is X, this is the magnitude of the earthquake. And let's say the unit is Richter. Okay. Richter scale, of course. And we have another variable, Y. And Y is, let's say, the depth in, let's say, in kilometers of the depth of this earthquake. Okay, so as you can see, guys, here, we don't have just one data value. We're going to have like pairs of data values. So we're going to have, so the data is, in this example, so we're going to have like two variables. There will be like variable X and the variable Y. So as I said, the X represents the magnitude of the earthquake, right? So X, let's say, is, for example, first earthquake, the X is, let's say, 2.9. So 2.9, that's the magnitude of the first earthquake, right? It's 2.9 Richter, okay? And the corresponding depth, Y, is, let's say, 5 kilometers, okay? So this is like the first earthquake, right? The magnitude is 2.9 and the depth is 5 kilometers. Now, next earthquake. So the magnitude is, let's say, 4.2, and the corresponding depth is in kilometers is 10. Third earthquake. So we have the magnitude is, let's say, 3.3, and the depth is 11.2 kilometers. All right, etc. So we have how many data pairs? We have 7. So then we have 4.5, and the depth in kilometers is 10. Next earthquake, we have the magnitude is 2.6 Richter, and the depth is 7.9. And then 3.2, the depth is 3.9 kilometers, and finally 3.4, and then corresponding depth is 5.5. Okay. So again, guys, here we don't have like just one data value, we have data pairs, right? So for example, for the first, this is your first earth quake. So this is the what we are saying is like the magnitude is 2.9, and we are saying the depth is 5 kilometers. Okay, that's your first earthquake, right? So etc. So how many earthquakes do we have here? We have a sample of so we have 1, 2, 3, 4, 5, 6, 7. Okay, so we have like a sample of 7. We have a sample of 7 earthquakes, right? And so again, for each earthquake, we have the magnitude given by X, and we have the depth, which is given by Y. Right? Does this make sense to you guys? So you see, so the question here. So what we are doing here, we are trying to see if. So the question, I'm gonna try to see if there is any relation or correspondence, or if there is any relationship or connection or correspondence between the magnitude, okay, and the depth of the earthquake. So the question here, and we're gonna try to answer, is the magnitude of an earthquake. Is it related? Okay. So here, so related. Okay, to the depth. Okay, to the depth below the surface at which the earthquake occurs. Okay, to the depth of the earthquake. So again, when I say related, I'm saying is there like a relation or connection? Like, is there like a relationship, right, between the magnitude and the depth? So that's what we're going to try to answer in this section. Okay. So the goal. So the goal here. So we're going to try to see if there is. We're gonna see if there is a connection or a relationship or correlation, okay, between the X and Y, between the variable X and the variable Y. Okay. So again, the idea here is that your data is given by data pairs, okay, not just like one value, but you have a pair, right, of values, the magnitude and the depth of the earthquake, right? All right, so before answering this question, if there is a relation between the x and y, or between the magnitude and the depth of the earthquake. So first, we're gonna try to represent data, right? We have the data. We have seen like different ways to represent data, using frequency tables, histograms, etc. But this case here is kind of different, because in this case we have data pairs, right? There's this x and there's a y. There are two values, right? There's this magnitude and there is this depth, right? So we're gonna use, so whenever we have like data pairs, we have like two variables, not just one. We're gonna use the scatter diagram to represent the data pairs. Okay, so first, so we're gonna represent this data. So first, we're going to represent the data pairs using what we call the scatter diagram. So scatter diagram, guys, I mean, the idea here is we're gonna have, because we have data pairs, right? We have two variables, x and y. So we're gonna have like two axes. There will be the x-axis and there will be a y-axis, right? So so in this scatter diagram, so we have, so we're gonna have two axes. There is an x-axis and a y-axis. So x-axis, that will be a horizontal axis, and the y-axis will be a vertical axis. All right, so let's do this. So let's graph the scatter diagram of our example. Okay, so this is my x-axis, and here, let's say this is my y-axis. All right, now what are the values of x? Again, the x, that's the magnitude, right? So let's see the values of x. So like the smallest value of x, as you can see, smallest value of x would be, any guess what would be the smallest value of x? So, I mean, as you can see, the smallest value of x, the 2.6, 2.6 actually. The 2.9, but then there's this 2.6. So the smallest value of x would be 2.6. And the largest value of x is 4.5. Okay, so x is, it's like between 2.6 and 4.5, right? So I'm gonna plot the x between 2.6 and 4.5. So like I'm gonna have, so let's say this is 1, this is 2, this is 3, this is 4, and let's say here's my, this is my, let's say 2.6. Okay. I can probably take a different units here. So let me just do it again here. So let's say this is 1, 2, this is 3, this is 4. So I'm gonna need 2.6. So this is 2.6, and then I'm gonna need 4.5, right? We said the largest value of x is 4.5, so let's say this is 4.5, right? Now, so there's 2.6, And then there is 2.9. So there's 2.6, there's 2.9. I probably it's better to have like a larger units here. You know what? I'm gonna just have a bigger units. So let's say this is here somewhere 2, and this is 3 here, and this is like 4. Okay, so let's say this is my 2.6, and then we have 2.9. Then next value of x would be, so we have 2.6, 2.9. Then next value, it's 3.2 and 3.3, 3.4. So 3.2. This is the 3.3, and let's say this is 3.4. And then, so 2.6, 2.9, 3.2, 3.3, 3.4, and then we have 4.2 and 4.5. Okay, so 4.2. This is 4.2 and then 4.5. Okay, so all you have to do, guys, is just to plot the x's, right, on this x-axis. Next, I need to plot the y's. So the y's, variable y, it's from like the smallest depth, or the smallest value of y. It's actually 5, right? You see there's 5, 5.5, but then largest value would be like 11.2. So it's like from 5.
The smallest one is actually 3.9.
So let me plot for 5, and then to 11.2. So let's say this is 5, right? Then this 6.
I'm sorry,
7.
Professor. I
Yes.
think there's a 3.9 on your y-axis.
Did I forget? Oh, thank you. I appreciate it. Thank you. Yeah, I forgot 3.9. Thank you. So let's say this is 4. This is 5, 6, 7, 8, 9, 10, and here's 11. All right. So as you said, so this is 3.9 right here. Then next value would be 5. So I have my 5, and then we have 5.5. So 5.5, of course, it's between 5 and 6. So here's my 5.5. And then next would be 7.9, right? 7.9, which is very close to 8. So here's my 7.9. And then there's 10, I think, 2 10s, and then 11.2. So 2 10s, and then this is 11.2. All right. Now we have to plot the points, right? So first point, it's 2.9 and 5, right? So if x is 2.9, then y is 5. So if x is 2.9, so here's my x. So my x is 2.9, then y would be 5, right? So we're gonna go up to 5, right? So that will be my first point, or my first data pair, right? 2.9, x is 2.9, y is 5. Next point, we have 4.2, and the corresponding y is 10. So 4.2.
Is that an old jive?
No, it's not, because ojive is supposed to represent, cumulative frequency, but it looks like ojive, right? There's like, yeah, it looks like ojive. But again, the scatter diagram is supposed to represent data pairs when you have like x and y. But
You know
you're
we
right.
have this in psychology.
Yep. I mean, but you're right. I mean, the idea is the same. Like it looks like a ojive. You have your data. You have your classes boundaries on the x-axis, and then you have your cumulative frequency on the horizontal vertical axis. So yeah, it looks the same. It's just
So when you're plotting, are you using those actual lines or no? They're not supposed to be there. You're gonna erase
no, they're not supposed to be
Okay.
there. I'm just trying to explain how I plot the points, right? But yeah, so the lines, I mean, I'm supposed to raise the lines here. So that would be my first point. Next point is 4.2 and 10. So 4.2, this is my 4.2, and so this is the point 4.2 and 10, right? And we need, of course, to raise the lines here. Next, 3.3 and 11.2, 3.3 and 11.2, 3.3 and 11.3 and 11.2, 11.2, it's right here. So this is my point right here. Then 4.5, 10, 4.5, 10. So 4.5, 10, this is 4.5, we're supposed to go up to 10, right? So we're gonna have this point right here. Right, and then 4.5, 10, and then 2.6, 7.9, 2.6. So this is 2.6, 7.9. So here's my 7.9 right here. Then, so the idea, guys, we're gonna use this scatter diagram to see if there is like a sort of a relationship between the X and Y. I'm gonna explain the possible connection between X and Y in a minute using this scatter diagram. Yeah, so we're gonna use this to try to guess if there is any connection between X and Y. So the next value is 3.2 and 3.9, 3.2 and 3.9. So 3.2, it's right here, and 3.9 right here. So we're gonna have this point. And finally, 3.4 and 5.5, 3.4. So this is 3.4 and 5.5. It's right here. Okay, so there's this point here. All right, so we got this is what I call the scatter diagram. So you don't connect the points, guys. Just plot the points, you plot the data pairs, and that will be your scatter diagram. So this is your scatter diagram. So scatter diagram. Okay, and again, don't points. You don't have to join the points. Okay, don't. Oops. Sorry about that. Yeah. So this is not like the ogive. In the ogive, you're supposed to connect the points, right? So here, do not join the points in the scatter diagram. Okay. All right. Now, so now we're gonna try to use the scatter diagram to see if there is any connection between X and Y. So the first possible connection or relationship or correlation between X and Y, it's called linear correlation or linear relationship. So the first, so we have so the first one possible, so one possible one possible relationship or correlation or connection between X and Y. Between X and Y is called linear correlation. So what's a linear correlation, right? So it's called linear correlation. So the idea here in the linear correlation, guys, is that the data, your data, which is represented by this scatter diagram, your data is going to resemble a line. Okay. So the idea here is that the data represented by the scatter diagram is going to resembles a line. Okay. Or in other words, there is like a straight line relationship between the two the variables. Okay. So in other words, there is a straight line relationship between the two variables, between X and Y, between the two variables, between the X and Y. Okay. And so the idea here is that when you have a linear correlation, the two variables X and Y, they change at a constant rate. Okay, so the idea here is that, so in a linear correlation, when we have a linear relationship, so in a linear correlation, the two variables, the variable, the X and Y, they change at a constant rate. Okay. So for example, let's say you have your examples. Okay. So first example, let's say this is here's your scatter diagram. This is your scatter diagram. And then let's say you have the following data. For example, this one here. Okay, this is your scatter diagram. Right, this is your scatter diagram. Okay, now you have all these points, right? The question is, so if you take I mean, the best line that represents this scatter diagram is the line that comes, closest to each point. So for example, like in this case, the best line probably is, I mean, it's just a guess. I mean, it doesn't have to be the perfect line, but the best line here would be, for example, which represents this data would be, let's say, for example, this line here. Okay. So again, the idea is this line here. The best line here would be the line. So the best line is the line that comes closest to each point, closest to each point. Okay, so like here in this example, I mean, the points here are, I mean, they don't lie like on the the same line, but still, you know, your line here, which is, you know, which comes closest to each point, is kind of, so we have a kind of a straight line here, right? So in this case, we have, it's not a perfect, you know, it's not a perfect linear correlation, but still you have kind of a linear correlation in this case, right? Because when you draw the line, which is becomes closer to each point, still you have like a sort of a, you know, you have a straight line here. So this is, so in this case, this is, so here we do have a linear, we have a linear correlation. Okay. So your line is, of course, in this example, your line is going up, right? It's not a perfect linear correlation, right? Because, you know, not all the points lie on the same on this line, right? But they are kind of, I mean, most of the points are very, very close to this line, okay, to this blue line. Now, in different example, so let's say you have a scatter diagram which looks like example 2. Example 2. So let's say we have like a bunch of points like this. Okay, so let's say this is your scatter diagram. Okay. So in this case, I mean, it looks like the data the data here in this case do not resemble a line, right? I mean, you know, if you try to draw a line which is kind of close to each point, you know, you're gonna have you have some points kind of far from your line, right? So in this case, the data do not resemble a line, right? So in this case, the data do not resemble a line. Okay. So we don't have a linear correlation in this case. Okay, there is no linear correlation in this case. So no linear correlation in this case. Okay. A perfect linear correlation would be when all the points they lie on the same lines. Example 3. So let's say a diagram, and then your points, they kind of okay, so this is your scatter diagram. So so in this example, I mean, if you try to draw the line which passes through the points, so you're gonna have, let's say, so like in this case, you're gonna have this line, right? And this one here. Okay, and as you can see, all the line, all the points, right? All the points that lie on this blue line, right? So here we have a perfect, this is a perfect linear correlation, right? Because all the points that belong to this blue line, right? So this is a perfect. So in this case, we say we have a perfect linear correlation. Okay, you see the difference, guys, between the perfect linear correlation and well, like in example 1, it's not a perfect linear correlation, but still it's a linear correlation, right? The example 2, it's clear that it's not the data that do not resemble a line, right? So it's clear in the example 2 that we don't have a linear correlation. Okay. But again, the idea is in this linear correlation is we have like a straight line relationship between your variables, between x and y. Okay, so if you have a kind of a straight line relationship between your data pairs, then that's what I call a linear correlation. Okay. So again, so what we are saying is, so if, I mean, we can take this as a definition. So if all the points lie, if all the points they lie on the straight line, on a straight line, like, so this is like example 3, like example 3, right? Then we have a perfect linear correlation, right? So then we have the perfect linear. Again, correlation means relationship, guys, or connection, right? Perfect linear correlation. Okay. Now, if you have like in this example 1, right? We said it's kind of it's a linear correlation, right? The data resemble a line in this example 1, and the line is actually going up, right? So in this case, if the line is going up, we say we have a positive correlation. Okay, so if the line, so like here in the example 1, because the line is going up, line here is going up, then we say we have a positive. We say we have a positive correlation or relationship between, X and Y. So if the line is going up, okay. So in other words, line going up means that the values of X, the values of Y increase as the values of X increase. So in other words, here the values of Y, increase as X increases. So if you have a line which is going up, then we say we have a positive correlation. We have a positive correlation or relationship between X and Y. Of course, if the line is going down, then we have a negative correlation, right? So 3. So if, oops, I'm sorry, I went over time. I'm sorry, didn't check the time. So let me just finish this sentence. So if the line is going down, then, I mean, the values of Y decrease. The values of Y decrease as X increase. The value of Y decrease as X increase. Then we have a negative. So we say we have a negative linear correlation. So we have a negative correlation. All right, I'm gonna stop here, guys. So next time we'll see how to measure. So that we're gonna use numerical measurement to see if there is there is a relationship or connection between the values of X and Y, and we'll see. We're gonna use again some numbers, numerical measurement to see if we do have a linear correlation or not. Okay. All right, I'm gonna stop here, guys. Thank you for listening, and I will see you hopefully next Monday.
All right.
Right.
Thank you, Professor.
Thank you. Thank you,
Have a
everyone.
good one.
Thank you,
Have
Edward.
a good one.
You too. Can I just stop recording?